My name is Raul Ravelis, and I work with Bond Pets here in Boulder, Colorado. Uh, I've been working in media and process development for about 7 years now. And before that, I did other jobs in science. For instance, I worked in a veterinary hospital. I worked in a chemistry lab, and I also worked as a field engineer for a geothermal contracting company. So I've had a varied career, and so today I'm here to talk to you about fermentation science and how I use SBI's Flasks to aid me in that process. So if you are here, then I congratulate you on taking on what I believe to be the most difficult job in the world. Fermentation science differs from other pursuits in that the interaction between physical, chemical, and biological phenomena must all be taken into consideration. Physical phenomena may include mass transfer considerations due to reactor geometry and mixing, the effect of pH salinity and pH on gas solubilities, and non-Newtonian broth characteristics. Chemical phenomena may include precipitation reactions due to solubility limits, heat and light reactions, and finally, the biological considerations: growth phase, growth rate, metabolic flux, osmolarity, shear tolerance, genetic drift, sterility, etc. So unlike most standard chemical processes, our system fights back, either through adaptation or mutation, and due to the capital cost of equipment and the long fermentation run times, it is often difficult to quickly produce sufficient replicates to determine whether results are statistically significant. Ultimately, our goal is to make more product, make it faster, and make it cheaper. So I will now go over some general principles I use to optimize media and show how SBI's equipment has aided me in that process. So first, we will discuss media optimization from a qualitative aspect, then go over the quantitative measurements which will guide our final media optimization. So the most important thing to understand is that you don't make more product by trying to make more product. You make more product by better understanding the system. So this is a statement that often upsets my managers and employers, but in the end, run times, cost of good reduction, and titers are all that matter. So the closer you can get to water, the better. So the more dilute the media, in general, the better your reactor conditions will be. So metabolic overflux, precipitation reactions, and foaming issues that occur in the lab generally do not go away when you scale. They get worse. So here's a slide showing some media stability issues that you may run into. So it's sort of a Venn diagram where you see overlap. There is an interaction that would be a precipitation reaction that would damage your media as you're preparing it through sterilization and or as it mixes in the reactor. So number two, you don't need as much as you think. So the fewer components you use is generally better. So you can reduce side reactions and increase the power of your design of experiment. So generally, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, iron, magnesium, and potassium is all that is required for most life. Bacterial and yeast, there may be some slight vitamin needs depending on your organism, and that is something you'll have to discover for yourself. But in general, most lab media have too many ingredients and are overly rich. So here's a slide showing different substrates, common sources, and this will be a key to your media development, as far as you will have to determine what carbon source is best, what nitrogen source is best for you, and also balance magnesium, sulfate, potassium, and all these micronutrients. So number three, concentration gradients help control flow and rates. So here we are concerned with the probability of a reaction occurring. So we understand that the concentration of either our ingredients or potentially metabolites produced by our strain or the product itself may affect the metabolism of our organism. And so then we can also use these gradients. We can also use these gradients to manipulate our metabolism and encourage carbon flow in a particular direction. So generally things like trace elements are not required, but they can be used to aid you in manipulating your metabolism in certain ways. So next, we will go over the solution. So here we see SBI's equipment. So these are flask readers, and there's a light source at the bottom, of course, and that light source uses refracted light as opposed to transmitted light, and therefore you can read optical densities or turbidity at much higher ranges than you can in traditional spectrophotometer readers, and therefore you will not require intervention via sampling. So we will now go over a specific experiment where I used a nitrogen limitation, where I performed a nitrogen optimization, and I will go over how I use these guiding principles to get quantitative measurements that will, in the end, allow me to produce my media optimization. So, number one, the closer we get to water, the better. So we need to determine the minimum amount of X that is required to achieve our maximum output. Here we are interested in growth specifically. So we will be looking at growth curves and growth rates, but your output could be your product or any other thing. So on the lower end, we are performing what is essentially a titration of nitrogen, and we are attempting to see what is the minimum amount we can add or we should have in order to achieve our maximum growth rate. So as you can see, it's a little bit difficult to discern growth rates when some of your curves overlap. So for that reason, sometimes I prefer to look at the derivative curve. So here we are looking at the change of growth rate over time. So our peak growth rate will be this first peak, and this will be our peak growth rate on our initial carbon source. So that would be glucose. And then we see our dioxic shift as our growth rate goes down. And then our second peak is our growth on our secondary metabolites. So we can track our metabolic flux in that. As we go through here, we can see that the high concentration of 0.6 is the only one that has a fast growth rate on the second peak. So we're probably already limited for nitrogen below 0.6. But at a lower concentration in the range of 0.4, we can see that we actually grow significantly faster. So if you're designing this for a batch, you would know that you would want a higher concentration, but for a fed batch, you would try to target this lower concentration. So now that we know to a degree what our ideal concentration for this nutrient is, we want to know how much do we need to add in total. So here we're going to determine the gram yield coefficient for our particular component. So this is the amount of grams of your ingredient required to produce X amount of cells in our case, but it could be product in your case. So what we did is from our previous experiment where we did a titration of low levels of nitrogen, we then took the cell dry weights and plotted grams of nitrogen versus grams of cell dry weight. And the slope of this curve is our gram yield coefficient. So this is the amount of nitrogen Sorry, this is the amount of cell dry weight produced per 1 gram of nitrogen in your broth. And keep in mind here, that number is 14.7 for us. It'll come back up later. Okay, so now we're going to look at the upper limit for our reagent to determine when we're adding too much of our ingredient and negatively affecting our growth rate. So on the upper end, here we're looking at the starting condition for our media. So this is a lab media, something like YPD, YNB, where you're starting at high levels of nitrogen. Here it's about 4.8 grams per liter. And we're looking to decrease that for cost of good reductions and also to eliminate the amount of nitrogen that goes into our wastewater after our fermentation is done. So here we can see that at the higher concentrations, the lag phase actually increases and our growth rate decreases. So we're not getting any assistance from all that additional nitrogen. And when we went back and looked at the data, it does not appear that our product formation decreases significantly with this reduction. So what have we determined so far? We've looked at our initial recipe concentration of 4.8 grams per liter. And we determined that, I think I might have skipped the slide there. Aha, I did not, sorry. So we looked at our initial concentration of nitrogen, and that is a little bit too high for our desired growth rate. We see a mu of 0.185 per hour. From our earlier titration, we see that our minimum amount of nitrogen required is somewhere in the range of 0.4 to 0.6, and our growth rate is faster than our original condition in our starting media. And next, when looking at the upper bound for nitrogen, we see that above 0.6, we start to see some reduction in the growth rate, and so that is probably our upper limit for this ingredient if we want to grow fast, so therefore it's something we might choose to feed. And finally, we determine a yield coefficient to figure out how much total nitrogen we're going to need for our process. And of course, the question is always, does it scale? So when we look at our original condition, here you can see the orange line is the predicted theoretical growth rate that we received from our Flasks experiment of 0.185 for our original condition of 4.8 grams per liter of nitrogen. The 4 blue dots here are our first sample in a bioreactor after a 24-hour grow out. And we see that our CGQ growth rate closely predicts our growth in the reactor. And then when we, key thing is the OD is about 20 here in 24 hours. And then when we ran our conditions for our optimized amount of nitrogen, we did notice a significant increase in the amount of mass we produce in that 24-hour period. And again, when we did this 4 times in 4 different reactors, we got similar results as were predicted from our Flasks experiments. So next, the nitrogen consumption. So the amount of nitrogen required per gram of cell mass produced was 14.7 as predicted from our Flasks experiment. And when this was carried into the reactor, we do in fact see that 14.7 is the amount of nitrogen that is consumed by our strain. Okay, so we have determined that our original recipe is about 8 times in excess for nitrogen, that this concentration is having a negative effect on growth in both the flask and the bioreactor. We have bracketed our potential mu max concentration, so the concentration at which we can achieve the maximum growth rate. where we can further test and optimize our nitrogen concentration for our process. We have determined that our strain grows faster at lower concentrations of nitrogen, and we know how much total ingredient will be needed to reach our target density, i.e. 10 grams of nitrogen for 147 grams of product. So this makes it easier to scale your media. We have a target value for testing limited reagents and excess reagent in our bioreactor. Since we know the need for a particular reagent, we can then easily run tests of nitrogen, iron, or phosphorus, or whatever limitation you may be interested in. So the question becomes then, can you do this without CGQ? And the answer is that with sufficient replicate sampling, weekends, long nights, eventually you will get this information. But in industry, it is a race, and the first to market and or profitability is generally the winner. So here you can see typical Flask sampling. So there's about four samples taken throughout the workday when there are plenty of staff around. And then there's this gap in the overnight period, but you can see that the resolution is relatively low. Whereas with our continuous growth quantifier here, we can track the entire growth curve. So we see our first part of our curve where we're growing on glucose, we see our dioxic shift, and then we can track growth on those secondary metabolites. So the great thing about CGQ is that it allows you to sample at specific points in your curves that may be of interest to you. So it may be that you are specifically interested only on growth on glucose, or only on growth on metabolites, or you may want to determine when is the best time to transfer your culture, when is the best time to sample for cryobanking in order to increase the viability of your cells. So the great thing about this piece of equipment is that once you have determined what the best time for sampling and or harvesting is, it is easy to hit that target again. And the great thing is that you don't have to be in the lab to perform this tracking. You can track it continuously and remotely, and then come into the lab at the appropriate time. So it is this remote tracking with reduced manual sampling that allows you to reduce labor cost and consumable costs, and long-term, of course, the reduction of material costs in your process is going to lead to cost of goods reduction, and hopefully along the process, you will be able to speed up your runs and increase your total yield. So conclusion, media optimization, I believe, is essential to process development, cost of good reductions, continuous bioprocess improvement, and sustainability. So CGQ offers better resolution that isn't realistically possible via traditional shake flask growth measurement methods. Flask data can be used to make accurate predictions of bioreactor behavior. And CGQ allows for consistent harvest and transfer of inoculum. And then finally, media optimization and process development can be made more efficient using the self-growth quantifier by SBI.